All right, IBAISL2. We're finally going to start our baby calculus unit. So today we're going to start using this word, derivative. By the end of this lesson today, you should know what a derivative is and how you can find a derivative from basic equations. First thing we need to talk about is that you're going to see this word in a lot, gradient. I think in my first year teaching IB, I ignored that word entirely because I was like, oh, it's just slope. I'll just use the word slope instead of gradient because that's confusing. But then when students took the IB exam, they were like, what does gradient mean? And I was like, well, probably should be using that word a lot more. You guys, gradient just means slope. That's all it is. It's just the British IB version of the word slope is gradient. Just some reminders about slope that you've seen before in previous courses. A slope is a rise over a run. A way you can find that slope if you're given two coordinates, like if you're given x1 comma y1 and an x2 comma y2, is that you can take y2 minus y1 over x2 minus x1. So it's the rises, because the rises have to do with the y's, and the runs, left and right, have to do with the x's. So it's the change in x over the change in y. It's another way we can put it. So many ways to define gradients, slopes. Another way that in like a lot of word problems and stuff that they'll talk about gradients or slopes is the rate of change. So slope, gradient, rate of change, rise over run, it's all the same thing. Now, this first example here, we're going to have to talk about some like pretty basic vocab. Well, not basic. We're going to have to talk about some new vocab. So, a tangent is a line that touches a curve in exactly one spot. So if I was to try to draw a tangent on this picture, here's your classic parabola, your y equals x squared. If I draw a tangent line, let's see. So I can move this line, and if I can get it like, if I go like this, do you see how it's crossing at two separate points? That is not a tangent line, but if I move it all the way like, so it's right there. So it's just touching in one spot. This is your visual for a tangent line. It's a tangent to the curve. The reason we're going to start using tangents is because derivatives really have to do with the slopes of these lines. So this line here has a slope. And I'm going to show you guys algebraically how you can figure out the slopes of these tangent lines at certain points to the curve. Now, if you picture that tangent line moving to another spot, maybe we'll do a different color, we'll do orange. If I try to do a tangent line like over here, like just make it barely touch the curve, pretend that's touching once. This tangent line is it's another tangent line to the curve, but has a completely different slope. It has a negative, sharper slope. And then as I move down the curve, like if I put in another tangent line right around here, so it touches just in one spot right here, then this tangent line is going to have a different slope than the previous one. And you can find tons of them. In fact, there's any point on the curve can have a tangent to that point. So here's another tangent. So yeah, they're just all these tangents that touch in different places. Now, finding the slopes of these, well, I'm getting ahead of myself. Okay. Now, the tangent only goes through the 1 point on the curve. If I go through 2 points or multiple on a curve, that's called a secant. So I'm going to draw a secant in here for you. Let me see what's the most optimal way to do this. Let's get it like going through right there. Okay, see how this touches the curve in two separate places? So this is a secant line. Now, if you picture me taking that secant line and then you do another one that goes through this point here, but then I sort of shrink the secant so it's going like, through these 2 points right here, and then I do another one that goes through like these 2 points, and then I do another one that goes like, if I just get like closer and closer and closer to this point right here, eventually that secant will just be a tangent because it'll come through and touch just at this spot right here. I'll make it really big. So if you sort of slide that secant, I guess I use like pink, this way towards the other point, eventually the secant becomes a tangent when you get those 2 points so close to each other that they are basically the same point, and then the secant becomes a tangent line. So that's what this statement right here is saying, that the gradients of a tangent is the limit of a secant. So the slope of a tangent line is like taking the slopes of the secant lines and then sliding them closer and closer together, so the 2 points eventually become one. The average rate of change between the 2 points is the same as the gradient of the secant between the 2 points. So if I give you 2 points on a curve, like if I tell you this point is x1, y1, and this is x2, y2, then you could say that the slope between them is y2 minus y1 over x2 minus x1. And then the slope between them is the rate of change between the 2 points. So it's really just like finding the slope, the gradient. Now, the instantaneous rate of change at a point is the gradient of the tangent at that point. Here's where calculus comes in. So if I go back to this diagram and you think about these 2 points, this diagram is going to get very messy. Like this point and this point, we can find the slope between those 2 points. It goes from here to here. Then if I move this point a little bit closer, like here, then we can find the slope of those 2 points. And if we move it yet again, we can find the slope of those 2 points. And then you move it yet again, we can find the slope between these 2 points. But then you get to this point where, like, if this point gets so close, like you're finding the slope between those 2 points. But what if I slide it infinitely close until it is the actual point, like both points are the same point? That's where your slope formula doesn't work. Because if you're trying to find the slope between a point and itself, like if you plug in x2 and x1 with the same number in the denominator, you get 0 divided by 0. So 0 divided by 0 is undefined. Now, that doesn't mean that the slope of the tangent is undefined. It means that we have to use some other trick to be able to find the slope of this red line right here, because you can find the slope of that tangent using derivatives. So the big point, like if a lot of that graph stuff was going over your head, here's the big part that we need to get down. The gradient function is called a derivative. Its notation is f prime of x. So if you're given a function like f of x, the derivative is f prime of x. It's got that little apostrophe on it. The derivative of f of x with respect to x, that's just kind of saying the same thing. This is f prime of x. If you take the derivative of f of x, the derivative is f prime of x. Now, what is a derivative? A derivative is basically just a slope machine. It's a function that takes in x inputs and spits out slopes. So you put x values into it, and then slopes of the tangent lines come out of it. So you input an x value, and it outputs out a slope of a tangent. So just to like picture that, say you have like some curve that goes, parabola or something like that, and then you take a derivative of that and feed in like a, let's say that this is 4 right here or something, then the slope of that tangent line is putting 4 into the derivative. Couple more notations for, and we're going to do examples of all this derivative stuff that make it more clear. Sometimes they don't write f prime of x, they write dy dx is another way that we can write derivatives. I'll do my best in the examples today to change it up and use them both. Now, the big tool we're going to be using today is called the power rule. This is the power rule. This is the power rule for taking derivatives. If you have a function in the form of ax to the n, then that little n comes out in front. So you take the n and you pop it out in front. So it lives out here. But then you have to subtract one. So I sometimes call this the pop and drop. Because you pop the power out front and then you drop it down one. Pop and drop. Let me show you an example. It's going to make way more sense if I start using numbers. For each of these problems, we're going to find the derivative and then use that derivative to find the gradient of the tangent when x is equal to 2. So, first, to find a derivative. The pop and drop method, because this is in the form of number x to the power of number, to the 2 power, the 4 comes out in front, so that's the pop. Then we have to drop it down one. So dy dx, which is just notation for taking the derivative, is 3 times 4 x to the 4 minus 1. So notice what happened. The 4 came out front. That's this process right here. And it dropped down one because you always have to subtract one off that's the drop part. So pop, bring it out in front, drop it down one. Then we just have to simplify this. So dy dx is equal to 12x cubed. Now, what did we just find? This is the slope machine for tangents to y equals 3x to the 4th. So y equals 3x to the 4th was the starting function. This is the slope machine of the tangents to that curve, y equals 3x to the 4th. The last part of all these questions is find the gradient of the tangent when x is equal to 2. So we put a 2 into that, and we'll say 12 times 2 cubed. Now 2 cubed is 8, so we get 12 times 8, so this is 96. So the derivative is this. This is part of our answer. This is the derivative. But then 96 is the slope of the tangent to the curve. When x is equal to 2. So we use the power rule to find the derivative. Then we plugged a 2 into it to figure out what the slope of the tangent would be at that point on the curve. Let's do it again. Same thing here. If you want to find the derivative, this time I'm not going to use dy dx. I'm going to use y prime. Y prime is still just a derivative. Same thing as like f prime of x. We do the pop and drop. So the 3 has to come out in front and then drop it down one. So this becomes 3 times 5x to the 3 minus 1. So y prime is equal to 15x squared. So this is the derivative. It's the derivative of y. That's part of our answer. Then when x equals 2, we're going to put a 2 into that. So y prime is equal to 15 times 2 squared. So this equals 15 times 4, which is 60. So then we can say gradient of tangent when x equals 2 is 60. Now, if there's multiple parts to your equation, like this part, this part, this part, you can just take the derivative of all those parts separately. So let's switch back to dy dx, just to remember we can use either notation. For each of those little algebra chunklets, we're going to pop and drop each of them. Now, you might think to yourself, like 3x to something doesn't have a power on it, but remember, there's a 1 power out in front, or up in the power spot. If you would just have a number on the end without an x, you can think of it like x to the 0, and then the 0 is going to come out in front. So here, let's do it. 2, pop and drop, 4x to the 2 minus 1. Then this 1 has to come out in front, so this becomes plus 3 times 1, x to the 1 minus 1. But then this situation is interesting with pulling the 0 out in front, because you're going to get like plus 0 times negative 5 x to the 0 minus 1 or something like that. But it really doesn't matter what comes after the 0, because anytime a 0 multiplies with something, you just get 0. So when we simplify this, we get 4x to the 1 power, which is just 4x. Then here, x to the 1 minus 1 is x to the 0. And x to the 0 is the same thing as 1. Anything to the 0 power is 1. So here we just get plus 3. And then this part totally goes away because of the 0. So this is our derivative right here. My gosh, this is getting sloppy. So that's the derivative, 4x plus 3. The sort of shortcut with that is that anytime there's just a number on the end without an x, the derivative of that just a number is 0. So it really just goes away. You don't even have to worry about it. So it's really just doing the pop and drop with the first chunk and the second chunk, because this chunk goes away. Now we need to feed 2 into this. So we're going to do dy dx 4 times 2 plus 3. And that 2 won't always be the same. It's just the same for these examples, but it might change. You know, they'll tell you what point to plug in. So that 8 plus 3 is 11. So 11 is the slope or gradient of the tangent to the curve when x is equal to 2. Okay, another like 3 little chunks happening here. So just do the pop and drop with the first 2, and then remember, if there's just a coefficient on the end, then it goes away. A constant on the end, not a coefficient, because the derivative of a constant is just 0. So y prime is 3x squared, because you do the pop and drop, plus 2. That's the other shortcut, is that when you have something x to the 1 power, the derivative is just the coefficient. So boom, there's our derivative right there. Then we got to plug in 2. $14. So gradient is 14 when x is equal to 2. Now, this is the first sort of like trick question, I guess. Before you take the derivative, anytime you have an x in the denominator, like anything that's in the basement, whatever power is on it, you need to move it back upstairs and make it a negative exponent. This is a property of algebra. And to be able to use the power rule, the pop and drop method, we have to rewrite it before you do any derivatives. So this becomes 2x to the negative 1 plus x to the 1. Now we can do the derivative where we can pop and drop the negative 1. So the negative 1 comes out front. So y prime is negative 1 times 2 x to the negative 1 minus 1. Remember, you still have to drop. Now this is interesting because you get a negative minus a negative, which means it's like a bigger negative. The derivative of x is just 1. So we'll just put a big +1 on the end. So if we clean this up, this becomes negative 2 x to the negative 2 plus 1. Now, anytime you have negative exponents, you need to put those back into the denominator. The same way that we pulled it from the denominator and put it up top and put a negative on it, we're going to do that backwards now and say y prime is negative 2 over x squared. Turn it positive because you moved it back downstairs, plus 1. Now when x equals 2, we're going to find the slope of the tangent. So y prime equals negative 2 all over 2 squared plus 1. So this is, we'll take it step by step here. Negative 2 over 4 plus 1, which is negative 1/2 plus 1 when you reduce your fraction. And then with a common denominator, we're going to have to do 2 halves here. So this is 1/2. So slope is 1/2 when x is equal to 2. Slope of the tangent. This last one is very similar, where you have to do a rewrite before you can do the pop and drop, where you got to move that x squared back upstairs and make it a negative. Then you can pop this guy out in front and drop it down. So this becomes, I guess I'll use dy dx again to be good. Remember, you can just interchange them. Negative 2 times 3x to the negative 2 minus 1. So this is negative 6x to the negative 3. So dy dx is equal to negative 6 over x cubed. That's the derivative. Then when x is equal to 2, we get negative 6 over 2 cubed, which, you know, if you don't really want to do too much work, I'm not going to take your calculators away. You can just punch that in a calculator and then hit answer to fraction. But I think this is negative 6 over 8, which is negative 3/4. So negative 3/4 is gradient. I'll switch my words all the time on you guys. Gradient of tangent to y when x is equal to 2. Last thing is just sort of a teaser about what's going to happen next lesson, but we're going to start talking about when the function is increasing and decreasing. Increasing, it just means like if it's going uphill, and decreasing means if it's going downhill, if you read it from left to right. You can figure out where functions are increasing and decreasing all by the derivative. So when the derivative is greater than 0, aka positive, that means that the original function is increasing. That makes sense because if you draw a picture like this, like any slopes of the derivatives over here are going uphill, and then like they're going uphill, uphill, but then when you get to the top of the hill, it's totally flat. So like over on this side here, this is all uphill, and then starting here, again, it's going to go uphill again, because here you would get a flat tangent, and then it goes uphill, uphill, again, and then in between them is where it goes downhill. So this is all downhill in between them, and any slopes of any tangents would go downhill like this. So when it's flat, or stationary is another word that they call that, that's when the derivative is equal to 0, and then any time the derivative is less than 0, like a negative number, that means it's decreasing, because negative slopes mean you're going downhill. Okay, you guys, good luck with your homework. Ask me questions in class.